All right. Okay, everybody face in front, please. Thank you. Okay, so we got what we call a linear system here. It's a system because there's more than one. Anytime you have more than one of something in math, we call it a system. So this is a system of linear equations, or a linear system. When we want to solve a linear system, we're going to talk about that. Now, before we talk about that, though, I want to talk about what it means to be a solution of just a single line. Let's just review some stuff here real quick. Let's look at this red line, and let's just scratch out a quick graph of that line. So there's the x-axis and the y-axis. Okay, now let's do just a little bit of review here. How do we plot a line, that red line? Yes, sir. Okay, one easy way to do it would be to solve for y, put it in slope-intercept form. So I could, if I wanted to, I could write this as, if I subtract x to the other side, I could write it as y equals negative x plus 1, right? And that's in slope-intercept form. So what's the slope? Now the slope is the number in front of x, right? That's in the form y equals mx plus b, right? Okay, so what's the m? Negative 1. If I see a negative sign in front of a variable, that implies a coefficient of negative 1. Okay? So m is negative 1. What's b? So that tells me if I want to plot a line, if I want to graph a line, the easiest way to do it is always to make 2 points and then connect and extend. So I know 1 point right away, don't I? I know that b is 1. And so on the y, what's b stand for? Y-intercept, good. So on the y-axis, I'll just go up to y equals 1, put a point there, right? And now all I have to do is make a second point somehow, and then I'll just connect and extend to make my line. How do I do that? Yes, sir?
Go down 1 over 1.
Okay, good. I know the slope is negative 1. Slope is rise over run. So if the slope is negative 1 over 1, I'm just going to drop down by 1 and go over by 1 to get... You sure? Okay, but now the rise is negative. The run is always positive. If I have a negative slope, that means the negative number goes in the numerator. So it's always going to be the rise. I go down in the negative direction, but I go over in the positive direction. Okay? So there's my slope triangle, and now all I have to do is just connect and extend. I can be tricky with this here if I want to, maybe. I could just go like, oops, or maybe I can't. How come that didn't work? Well, that didn't work at all. I don't know. Boards. What's that?
I think you tap it and then you just pull one end down.
Is this different than it used to be? This board it's acting weird today. I don't have to be fancy, I guess. I'll just draw it. That's not the way it worked. Last year I could just put it on. I don't know.
It's perfectly straight.
Almost. Good enough, huh? So there's my almost perfectly straight line. Now, okay, if I want to find a solution to that red line, what's that mean? That's one example of a solution. If we take the point, I'll tell you what I mean by that. If I take the point where it crosses the y-axis, that has coordinates x equals 0 and y equals 1. Now what happens if I plug those values into my original equation? I get 0 plus 1 equals 1. Is that true?
Yes.
Yes, it is. So that is a solution. It's a solution because it's a value of x and y that satisfies the red equation, makes it true. Can anybody think of another solution? Janelle, hand went up. Almost.
Isn't it like an infinite number of solutions?
Yeah, there are an infinite number of solutions on that red line. Because as it turns out, look what happened here. This solution with coordinates 0, 1 corresponds to the 1 point right there. Now, how many points are strung out along that line? Infinite number. Every one of those points has an ordered pair, right? X and Y coordinates that define where it is. Now, they fall into a pattern. It's a line, right? But there still are an infinite number of pearls on that string, right? Points on that line. What's another example of just one of the infinite possible other points that we could choose to look at as a solution? 1, 0. Sure, here's another point right there with coordinates 1, 0. And sure enough, 1 plus 0 equals 1. Check. It's true. How about if we go down one more and over one more? What are the coordinates of that spot? -1, +2. Sure enough, -1 plus 2 equals 1. They're all going to work, aren't they? So there are an infinite number of points on that line. Each of them has an ordered pair that acts as a solution. Now, what about the blue line? Okay, if we graph the blue line, let's do the same thing we did before with the red. Let's maybe get rid of some of this red stuff here. It's bogging things down, cluttering the board. I'll leave those on. Okay, so if I isolate the y, I could subtract x. How do I get rid of that negative sign? Divide or multiply. Either way, both sides by -1. It's probably easier to multiply. If I multiply both sides by -1, I'm going to get y. And what's going to happen to this side if I multiply the whole side by -1?
They're going to be opposite.
Good. Changes the signs. So it looks like I've got a slope of 1 and a y-intercept of -2. So there's my y-intercept. I'll go up 1 over 1, right? And there's my line. Okay. How many?
Excuse the interruption. Randy Vinthorpe, would you call extension 3804?
How many solutions on the blue line? An infinite number. Okay. But if we're trying to solve the system, we're not looking for all of the solutions to the red line and all of the solutions to the blue line. What are we really looking for? Yeah, we want to find all of the places, or maybe just the place, where the coordinates work in both lines at the same time. I want to find a simultaneous solution, a value of x and y that works in both the red case and the blue case. And where would that be? I think I heard it. Where's the one place where I'm going to get coordinates that work for both? At the intersection, right? So that's in effect what I'm doing. If I solve a linear system, I'm finding all the places where the lines intersect. Now let's think about this in advance here. How many times can lines cross? One. Can anybody think of a case where they don't cross once? Parallel lines cross how many times? None. Okay. What's the other possible case? Same line. If they're the same line, they cross an infinite number of times. They overlap everywhere, right? Okay, good. And we got the idea. I think we're set here. Let's take a look real quick at this guy. And nothing's working right today. Hopefully, okay, I kept my pen. That's good. Okay, so we want to take a look real quick, review two different ways that we can solve a linear system without graphing it. We want to try to find the intersection, find the solution without graphing it. Okay. Tyler, can I get you to turn around? Thanks. Okay, so the first one, substitution. You might remember this. Substitution is the method that works if we have what's called a naked variable in the system, meaning a variable. Let me define that real quick. That means a variable that either has a coefficient of 1 or -1, a variable that's really easy to isolate. So, for example, in this linear system here, which variable is the easiest to isolate? We want it out right there, that guy, isn't it? That x on the bottom, because it's by itself. It has a coefficient of 1. So all I have to do to get that x by itself is what? Subtract 2y, no big deal. Right? So I'm going to do that. If I subtract 2y to the other side, I get my substitution equation. And for some reason, I keep losing the ability to write on this thing, which drives me nuts. But I would have put a box around that. Okay, because we're going to come back to that. Whenever you get a substitution equation, you isolate a variable so that you can substitute it, put a box around it, it's useful, you'll come back to it. Now what are we going to do with that? Once I isolate the x in the bottom equation, where do I substitute? Do you remember how that works? In which equation? The other equation, good, the top one in this case, right? We're going to take everything, the x in the top equation that's being multiplied by 3, we're now going to trade for that negative 2y plus 2. Now think why we're doing that. Think in terms of strategies in math. What's the point of that? Well, the problem with that top equation right now is I can't solve it by itself because it has 2 variables in it. It's got 2 different kinds of variables. But if I trade that x for a bunch of y stuff, I will only have y's in the top equation. That's going to become a problem like we did yesterday. Like all that stuff we worked on yesterday, that's pretty easy stuff, right? So if I make that substitution where I used to have an x, I'm now going to have a 2y plus 2, that quantity. That's a relatively easy thing to solve. How would we go about solving that? This equation here that involves the y's. Distribute, add like terms, and then just isolate the y, right? If we do all that stuff, like we did yesterday, we're going to get the answer y equals 5. Now that's half the battle. That tells us the y location of where the lines cross, but I got to find the x coordinate also. So what do I do to find the x coordinate? I plug that y equals 5 back into right there. Now I could plug it into anything up here, but I've already, that's why I was going to have you put a box around this, because look, it's already built to figure out what x is. If I plug the value of y into that, there's a formula built in to calculate x, right? So I get, if I plug y in,
All JV girls soccer players
5, and that's easy. Negative 10 plus 2 is negative 8. We got it. Now we're done.
Soccer players.
Okay, we got both parts. We got the x part and the y part. And there's our ordered pair. That's the point where they cross. Okay, one last point with this. Now, how do we check to see if we did it right? Plug it back into what? Which equation? Top one. Okay, if I plug it back into top one, isn't that going to tell me, and it works, isn't that going to tell me that this point sits on that line? Does that mean necessarily that it's the point of intersection, though? What else do I have to do? Plug it in the bottom one. Because if it works in both of those, then it has to be the point of intersection, doesn't it? Right? Okay. So we'll skip through that. That's what we would do. Substitute into both. Okay, now, sometimes...
Sorry for the interruption. JV girls soccer players need to go to the student parking lot near the old gym to board their bus.
Okay, sometimes it's not convenient to substitute. Sometimes we don't just luck out and get a coefficient of 1 or negative 1 in the system. And then we don't want to substitute. It's hard. We have fractions to deal with and it's pain. So we do something else. We're going to do linear combination, or it's sometimes called elimination method. What we do with this is we're going to multiply one or maybe even both of the equations by a constant, distributed all the way through both sides in such a way that we can get the coefficients of x or y, either or, doesn't matter, to differ only by a sign. So for example, I'm going to get like a 12x in the top equation and a negative 12x in the bottom equation. Or I'm going to get a 35y in the top and a negative 35y in the bottom, something like that. Once I do that, I can add those up vertically, and those variables will cancel out. I'll get rid of them. That's the whole point. I want to eliminate one of the variables so I can get a simple equation with only one variable left, right? That's a lot of talking. Let's see it happen. Then I'll just substitute back and figure out what the other one is. So what about with this system right here? Do you see a way that I could, ideally, I could just multiply maybe one equation by something so I could get the variables to line up to cancel? Yes, sir. Okay. I could multiply the top one all the way through by negative 2, right? And if I do that, if I distribute the negative 2 all the way through each term, don't I get that? Right? Bottom one we can leave the same, because look what happens. The negative 4x and the 4x now are lined up to cancel, right? So when I add those two equations together, the x's go away, 8y plus negative 5y is 3y, negative 26 plus 8 is negative 18, and it's easy to solve for y, right? Once I've solved for y, I got to go back and find the corresponding value of x. Where do I substitute that value? Into, yeah, either of those. Either of the top two equations. If I'm just trying to find, if I'm substituting to find the value of the other variable, it doesn't matter which equation I use, because it's going to work in both of them, right? So we'll pick the one that's easiest. In this case, that's probably, the top one seems to have littler coefficients, so probably the top one, but it's not much difference. Sometimes it will be, though. So if I plug negative 6 in for my y, I get a really simple equation to solve for x, right? I get 2x plus 24 equals 13. So subtract 24, divide by 2, and after all the dust settles, I get that. Negative 11 halves. Now I got the whole thing. I got the x value and the y value, and we're done. Okay. What about one like, oops, didn't want to do that. What about one like that? Now this time, it's a little tougher, because I can't just multiply one equation this time. I've got to multiply them both. There's nothing I can multiply 8 by to get 12, other than a fraction. I don't want to do that. Or I could multiply 5 by to get 7. I'm going to have to multiply both equations by something, but I want to choose the smallest numbers I can. So what are those going to be? How can I create a number of x's or a number of y's that's the same number but opposite sign in the two equations? What do you think? Neil?
Times the top by 5 and the bottom by 7.
That would work. If I multiply the top by 5, I'm going to get 35x. Multiply the bottom by 7, I'm going to get negative 35x, and those would cancel. That's absolutely going to work. Now, are there numbers smaller than 5 and 7 I could use for the x's? Or for the y's, sorry? And that would be fine. It'd work. See it? Go ahead. Multiply the top by 2, that's going to give me a negative 24y, bottom by 3, and get positive 24y. That might be just a little bit easier because I'm multiplying by smaller things. So let's see what happens. If I multiply the first one by 2, I get all those, it distributes to give me all those terms. Multiply the bottom equation by 3, and I get all those terms, but the important thing is the y's line up to cancel. So when I add those up, the y's go away. 14x plus negative 15x is negative 1x, or negative x. Negative 44 plus 42 is negative 2. So I just multiply both sides by negative 1, and we got it. We got our x value. Plug it back into either of the first two. Doesn't matter. They're choosing the bottom one, that's fine. If I substitute 2 in for x, I get a simple equation to solve for y. Right? Find y, and I've got my ordered pair. I could check it by plugging it into both. If you just want to test, you want to do that. Make sure you get the right answer before you hit submit. Okay, now what about this one? I'll go real quick. If I substitute here, if I isolate x in the top equation and substitute, something weird happens. When I substitute that into the bottom, look what happens. I get 4y plus 6 minus 4y equals 7. Well, 4y minus 4y, those y's cancel, and I get an equation, or I get an answer that's weird. It's goofy. 6 equals 7. How do you interpret that? No solutions, right? That's what we said yesterday. If we get a goofy answer that's always untrue, that's never true, there are no solutions. Well, what does that mean in terms of intersections of the lines? What kinds of lines must they be? Must be parallel. If they never intersect, they've got to be parallel, right? Okay, what about this guy? Same kind of thing. If we use elimination method, multiply the top by 5 and the bottom by 2, so the y's line up. Y's line up to cancel. I end up with everything cancels. Look at that. The x's go away, the y's go away, the constants go away. I get 0 equals 0. What does that mean? What did we say yesterday? Okay, it's always true, so there are an infinite number of solutions, so they must be the same length, right? Make sense? Okay, that's pretty fast, but I want to get you working on it. If you have questions, we get those answered. But
Let's see if we can get a little bit of work done today.